Morning, everyone. It is my pleasure to introduce Toby Isaac as today's speaker in our seminar series. So a little bit of background. Toby earned his PhD at UT Austin, supervised by Omar Gattas, where he was working on algorithms for parallel adaptive mesh refinement, as well as scalable methods for forward and inverse products and ice-sheet modeling. Then he spent his postdoc time at the University of Chicago, mentored by Apley, assistant professor at Georgia Tech. And he is also one of the authors of the parallel AMR library, pForest, and has major contributions to PETSI. So I'm looking forward to this presentation, and the word is yours.
Okay, so this is a version of a talk I gave a month ago that was for the Lands group at Argonne. And that version of the talk, I tried to talk more about the software side of the finite element things that I've been putting into PETSI. But with such a finite element focused audience, I thought this would be a good opportunity to take a look a little bit at sort of the theoretical aspects of that talk in a little bit more depth. So the topic today is geometric decomposition of finite elements, which is something that's kind of implicit in a lot of implementations, but maybe not thought about directly. And so I'm going to start out saying what exactly we mean by that and showing a way that we can do this process of geometric decomposition for a large family of finite elements in the finite element exterior calculus using just a few constructors. So just to give a little bit of background, through my PhD, and I was also still located in Austin for my postdoc, I did some work using like Taylor-Hood elements for Stokes, but that was about as complicated as my finite element thinking got. I had you know, a murderer's row of talent available to talk to. Arbogast, Babushka, Demkovitz, Hughes, Odin, Wheeler. That's just in alphabetical order. I'm sure I'm leaving people out. And then when I got to Atlanta, I decided to say, hey, mixed finite elements are fun. Why don't I start thinking about them? So I kind of go about these things backwards. I'm a bit of a neophyte to some of these things, so I'm hoping that there's a chance that you know, having this audience, I can get some good feedback on some of these ideas. So like I said, I will start out by describing geometric decomposition and the subject that we're probably all very familiar with, just working in scalar polynomials. That's probably a good common basis. Then going to mixed finite elements, building up a background of the tools that we use when we do exterior calculus with simplicial finite elements. And then once we have that background, I'll introduce a way of doing an isomorphism between trace-free and unrestricted functions or differential forms. And similarly, I'll introduce an extension operator. I really do work better if people provide feedback over the course of the talk. So feel free to unmute, or if there is someone who's monitoring the chat, if people want to type stuff. I can't actually see that on my screen right now, but would be happy to pause and go into more depth or clarify as things come up. So let's get started. So geometric decomposition is this basic task for finite elements. So here we're just working in scalars. So I have some function lowercase f that is defined here on the edge of a triangle. And what I want to do is I want to find some function uppercase f defined in the interior of the triangle, which when I restrict it back to that edge is the original function, and which when I restrict it to the other edges is 0. So for me to be able to do this, lowercase f has to be trace-free. It has to be 0 at these vertices at the corners of the edge. So that much is obvious. And if whatever method I choose to define uppercase f from lowercase f is a linear operator, then what I've got is an extension operator that can take anything from the trace-free functions on the edge and define a function in the interior of the triangle. And either explicitly or implicitly, all local conforming finite elements are extensions of trace-free functions. We probably don't think of hat functions that way, but that's one way to phrase them. And that's what all of the various bubble functions that we use in higher order scalar finite elements are. And so these operators are lurking in a lot of finite element analysis, the trace-free construction and the extension operator. Okay, so observation 1, my function little f on the edge, if it truly is smooth, then it has to be expressible as the product of a smooth function, I'll call it f tilde, that's not necessarily trace-free, and the bubble function for that edge. Just multiplying them together gives me back my original function. So there is this one-to-one correspondence by multiplying by the bubble function between these unrestricted functions, no restrictions on the endpoints, and the ones that actually reach the value of 0 smoothly at the corners. Okay, and multiplying by that bubble is the transfer back and forth between the two spaces. So you can think of multiplying a unrestricted function by a bubble as an isomorphism. And it's not only an isomorphism, it's an isomorphism that's actually defined by an inner product, right? So the inner product of the unrestricted function with the restricted form looks like a weighted inner product defined on the unrestricted function. So that weight function is useful if we're trying to define orthogonal or biorthogonal sequences of functions. Okay, observation 2 is that any projection operator that maps the closure of the triangle to the closure of the edge is going to define a pullback. So a mapping from smooth functions on the closure of the edge back to smooth functions on the closure of the triangle, simply by you evaluate the pullback at x by evaluating little f at the projected point, right? So this is a pretty basic operation, shows up all the time in the analysis of finite element methods. And the thing to notice that even though little f is trace-free, it reaches 0 at these corners of the edge, it's not actually trace-free on these opposite edges of the triangle when we do this pullback. So the pullback alone is not enough to create a geometric decomposition. One reason why these pullbacks are always used is that whenever the function space that you apply the pullback to is affine invariant, then the pullback preserves the space. And since all of our finite element spaces are affine invariant, this is very useful for creating extensions when we don't have to worry about some kind of a zero trace condition. And so to put it all together, there is a way that we can construct this extension operator for any function on the edge, which is we take its unrestricted representation, and we extend that into the triangle. And then we multiply by the triangle's version of the edge bubble, which is the product of the barycentric coordinates for the two corners of the edge. And that gives us a function that is smooth in the interior, vanishes at the opposite edges, and has the appropriate trace on the original edge. So this is one way to do finite element geometric decomposition. One thing I like about this approach is all of the operators work pointwise. So the extension of f can be at x can be evaluated by evaluating the projection of a point of f tilde, which itself can be evaluated just by evaluating f if we need to. So this approach is universal, and it's already pointwise, I said. So it works not just for polynomials, it works for all smooth trace-free functions. We don't have to worry about a particular basis to represent the functions on the edge in the first place. And because of that, it's also composable. So if you need a basis for the trace-free polynomials, you can use a basis for the unrestricted polynomials and just multiply by the bubble function. And if you need a basis for the edge, you could do likewise. And so in code, if you're working, for instance, in Python, this lets you get a lot of reuse out of things that you've already done. You can use a decorator pattern to construct a trace-free space out of an unrestricted space where you just compose the evaluation. Likewise with the extension, if you throw in that projection operator. So this method is fairly universal for trying to do geometric decomposition of scalar functions. But there are good reasons to use other strategies. Universality is not the only thing we care about. So for instance, if your finite element implementation simply defines your finite elements by defining the functionals and then uses like an inverse Vandermonde matrix to a stably evaluatable basis, then you don't actually explicitly form the extension operators. So you wouldn't necessarily need these tools for that. If you've got a code that uses a Bernstein basis, well, you would use that approach. It's nice because it's symmetric. You've got some low complexity sum factorization operations for your finite element tabulations and things, but you've got some poor conditioning to scale with. And if you use like a Dubner type method where you're taking warped products of Jacobi polynomials, that's a different type of extension of geometric decomposition. You've got a good condition number. You've got similarly good low complexity, but with maybe some higher memory traffic. But your basis is asymmetric. So there are different approaches and there are trade-offs for all of them. So don't take my focusing this talk on the universal bubble times a pullback to be a normative statement that that's what every finite element code should use. Okay, so that's all scalar functions. So what about H-curl and H-div conforming spaces? I was working on writing this code up, and I was asking myself these questions. Is there a similar operation to just multiplying by the bubble that defines the isomorphism between the trace-free bubble functions and some unrestricted functions? Is there an operator like that that acts pointwise? Does it define a nice inner product with a weight function that I can use to define orthogonal or bio-orthogonal sequences of functions? And once we ask about that, we can also ask, okay, is there also an extension operator that is somewhat universal, that acts pointwise, that will give us geometric decompositions of the finite element spaces in use? And finite element spaces in use is quite large, but what I'm using this as code for is I'm using this as code for the standard full polynomial bases and the trimmed polynomial bases, which I'll discuss more in the coming slides. So this really is the topic of today. Geometric decomposition for mixed finite element spaces, hopefully in a way that is universal, so that you can define one set of operators that work everywhere. Now, when we're talking about trying to unify h-curl and h-div, we might as well start talking about exterior calculus, where these different mixed finite element spaces are all just part of a graded algebra. They kind of coexist together in a larger thing called finite element exterior calculus. So that's the analytical framework that I'm going to use to try to develop these operators for geometric decomposition of mixed finite elements. So this is all in a preprint that I've got up on arXiv, and barring some major things that have kept me busy the last couple of weeks, I've been trying to get it submitted. I'll hopefully get that submitted soon. Okay, so the idea of finite element exterior calculus, I think it's gained a lot of popularity, particularly in people who work in finite element libraries have at least seen it. But the operators that I'm going to construct are going to take advantage of some of the constructs, the tools for exterior calculus that are particular to simplices, triangles and tetrahedra and so on. So I want to make sure that when I use that notation, everyone is clear on what's meant. So here's a little bit of background. So we have the de Rham cochain complex, right? So H1 grad goes into H curl, curl goes into H div, div goes into L2. The range of one arrow is the null space of the next. That's what makes it a cochain complex. And the modulus of the null space by the range is the cohomology of the domain, right? So those are only non-zero if we have voids or handles or multiple pieces for the domain. So this is the major organizing principle behind mixed finite elements as written in vector calculus. And the approach to doing finite elements with these spaces is if we have conforming approximation spaces, here with lowercase h being the mesh constant, and some projection operators that commute with the differential operators on the arrows, then we have stable mixed finite elements. And we expect convergence of our finite element approximations. And this describes the Ravière-Thomas elements, the BDM, Nedelec, more recent Arnold Awanu. So this diagram of the commuting operators working on the cochain complex describes half a century of finite element research. And the finite element exterior calculus recognizes that vector calculus cochain complex as equivalent to one in exterior calculus. So now we no longer have scalars and two versions of vectors. We have all these things that are differential forms. And we have one operator, one differential that maps from one level of the graded space to the next. And the projection operators are all kind of described in the same terms as well. So even if you're more comfortable in the vector calculus setting, this should still be very familiar. Right, and so here's a quick cheat sheet for people who haven't looked at exterior calculus recently. The main things we need the differential as I described above. The differential is grad acting on scalars. It's curl acting on one set of vectors. It's div acting on another, and it's the zero operator for n forms, the volume forms. The other thing that we have is a wedge product, which takes a differential form of degree j and one of degree k and adds them together to get a differential form of j plus k. And most of these are just multiplying one scalar by something, but the ones that aren't are, for instance, the wedge product of two one forms is like the cross product. And the ones that I want to bring attention to are the ones on this diagonal where j plus k is equal to n. So this is the case where you're taking two forms and you're making a volume form. And so a volume form is equivalent to a scalar. And so these are all examples of kind of a duality. There's a duality between the algebraic k forms and the algebraic n minus k forms. That kind of plays a big role in a lot of what follows. So here, for instance, the one forms representing vectors and two forms representing dual vectors. We can take the dot product of them together. It's a scalar in vector calculus, but really what's going on in exterior calculus is you're making a volume form. The pullback operator is going to have all of the various Piola transforms that we use. The covariant for one forms is like the pullback of H curl conforming, and the contravariant for two forms is like the pullback of two forms is like the contravariant pullback of H div conforming spaces. And very important today is the Hodge star operator, the idea that an algebraic K form and an n minus K form really kind of represent the same information. The Hodge star can be thought of as kind of a signed Riesz map between these two. It takes, this two form that represents a plane in 3D and maps it to the orthogonal normal vector and vice versa. So again, this duality between k and n minus k forms is going to be very useful for the constructions that I'm going to show later on. Okay, I'm going to use some abbreviated notation that should be familiar to people who've looked at the work that Arnold, Falk, and Winther have done in some of their initial papers and books on exterior calculus. The idea being that, for instance, if I want to construct a canonical basis for algebraic forms, I can use the differentials associated with the different coordinate directions and representing them with a parenthesis and some kind of a subset, or if you want to think of it as an increasing map, helps me define all of the define an orthogonal basis for that space. So for instance, if I were working in 4D, like if I were doing space-time elements, the bases of the two forms would be the wedge product of x1, x2, x1, x3, x1, x4, and 2, 3, 2, 4, 3, 4. So these are all kind of the binomial 4 choose 2 things that you can construct. And then when you apply the Hodge star, you can think of the Hodge star as mapping every one of these wedge products to the omitted indices. So it's going to send dx1 wedge dx2 to dx3 wedge dx4 and so on. So if you end up implementing the exterior calculus in code, this is pretty much always going to be the basis that you'll use for your algebraic K forms. Okay, so that is all just finite element, or I guess that's all just exterior calculus without reference to any particular element. What about when we're working on a triangle or working on a tetrahedron or generally a simplex? Well, we've already seen the bubble functions, and those bubble functions are the products of these barycentric coordinates, which are 0 at the opposite vertices and 1 at the vertex it's defined for. So these look like just hat functions. And if we multiply them together, we get bubbles. But if we take the gradients of those, we get some one forms that are very useful because they transform the correct way as you do different type of transforms of the triangle, like from the reference triangle into the physical triangle, or the reference tetrahedron into the physical tetrahedron. So for instance, d lambda 0, which was always going to be 1 at vertex 0 and 0 at the others, it's always going to be orthogonal to the opposite face. And so these are covariant one forms here. And the same operation is happening here with this tetrahedron that's going between equilateral and right tetrahedron form. So they make a pretty natural basis for the one forms. And by extension, using the same type of wedge products as we saw for those coordinate one forms, we can construct sets of k forms for any k. So for instance, if I want to construct some two forms associated with the tetrahedron, for each edge, which has two vertices, I can take the wedge of the d lambdas for those vertices. So in this case, d lambda 0, d lambda 3. And it will always construct a two form here represented by a parallelogram, which is now going to transform contravariantly. So it's not always going to be exactly touching these corners when I center it at the centroid. It's going to transform with the tetrahedron. So because they transform as you go from reference to real, they're very useful for defining operators where you don't have to worry about the particular coordinates used. But the barycentric k-forms are overdetermined. Because there are n plus 1 vertices of the simplex, we've got n plus 1 choose k of these things, and they're in a space of dimension n choose k. So they're not a basis. If you want to talk about them algebraically, we can call them a frame as opposed to a basis. And the last construction that's really important for working on a simplex when we're working in exterior calculus are the Whitney forms. So given any of the boundary simplices of a triangle or a tetrahedron I'm working with, each boundary edge, for instance, is the hull of some subset of the vertices. We'll represent that subset as sigma. And then the Whitney form is a k form where k is the dimension of the simplex. So for instance, this one edge, it would be a one form. It's always a degree 1 polynomial. And it has this really nice property that if I take the trace operator, which restricts to an edge and also restricts to the tangential component, then it is the Kronecker delta. It's 0 on all of the edges except for the edge that it's defined for. So here we have the Whitney form 1, 2 between vertices 1, 2. Its restriction to this edge will be 1, and its tangential restriction to the other edges will be 0. And this shows the H-curl version of it, and on the right, the H-div version. Same idea. So once we have Whitney forms, there are many ways to define the two big families of finite elements, full and trimmed, but one of the most convenient ones for this talk is to say that the space of full polynomials on a simplex is going to be products of scalar polynomials with some of those barycentric k-forms. So those are constant over the simplex. And this should be trimmed. Let me make that trimmed. The trimmed polynomials are going to be the products of scalars with Whitney forms, where the scalars are 1 degree less. And that lambda should be a sigma. Let me fix that. Okay, so here we go. We finally got it. So this is the main difference. We can think of every full polynomial as a product of this form, and every trimmed polynomial as a product of this form. And the full polynomials, those are going to be our BDM, our Nedelec of the second kind spaces. Our trimmed polynomials, those are going to be our Raviart-Thomas or our Nedelec of the first kind spaces. And even though they have these spans in terms of different things, barycentric versus Whitney, they're nested, right? So the trimmed 1 polynomials are a subset of the 1 polynomials, subset of the trimmed 2 polynomials, and so on and so forth. So we often use these different constructions, but it's important to understand or remember that the same function could be represented either way, depending on the nesting of the spaces. And so all of this is then, the finite element exterior calculus as a research program has produced things like this periodic table of finite elements, which organize the trimmed polynomials and the full polynomials into these families based on dimension and degree. Okay. One thing that, if you haven't worked with them, may be a little bit counterintuitive with these, HDiv, H-curl conforming spaces, is that trace-free is not the same as vanishing on the boundary, right? That's the result of the reduced continuity between the spaces. So here we have, for instance, an H-curl function that is trace-free, even though it is clearly not 0 on this edge here. And it is lambda 1, lambda 2 times d lambda 3. You can do the same thing with Whitney forms. So here's a product of a Whitney form, phi 1, 2 with lambda 3. That's another trace-free function. And that's their HDiv encodings. And here are their, these are those H-curl encodings. And below we have the HDiv encodings.
Excuse me, Toby. This is
Yeah.
Nathan at Lawrence Livermore. I just want to say, first of all, these visualizations are so incredibly helpful, at least for me, at understanding what's going on inside this element. So thank you for that. And also, how do you make them? They're great.
So this is a Julia notebook. So this is all Julia plots.
So it's a Jupyter notebook with Julia as the language.
Yeah, and so if you go to the link for the slides, there's a related
Available
note.
after the talk. Ooh.
Yeah. So you can do. There's a FEEC-GIFs notebook. So I had to build a small exterior calculus implementation, and you can see how these things are constructed. Yeah.
Wow. Great. Thanks so much. Really appreciate it.
Mm-hmm. Okay, so I guess the thing to notice, okay, so here's the 2D version. We can go to 3D and see the same thing where we've got not vanishing but trace-free. And if you take a look, you'll notice that a pattern that we had in 2D continues, where we see every vertex number appearing either as a bubble index, lambda 1, lambda 2, lambda 4, or as a form index, d lambda 3. Likewise here for the Whitney form, we've got lambda 1, lambda 2, and the Whitney form is indexed 3, 4. And so before I get into kind of the new stuff, so all of this stuff you can find in sort of the original monographs from 2006 or so from Arnold, Falk, and Winther, is that our basic recipe for constructing a trace-free K-form is you either take a barycentric K-form or a Whitney form, and you multiply it by a bubble function with complementary indices. So anytime we see something that looks like bubble sigma star d lambda sigma or bubble sigma star phi sigma, that's trace-free. So this was all the setup of the background, visualization and notation for these constructs. And I'm going to kind of get into the new stuff, but I wanted to maybe pause here to see if there are any other clarifications that I can make. Okay, so not hearing any requests for that, let's forge ahead. Okay, so let's talk about that trace-free unrestricted isomorphism. So again, the scalar case was unrestricted times bubble is equal to trace-free. And we want to come up with something similar for HDiv and HCurl. So I'm going to kind of describe the way that these isomorphisms were presented in the literature, kind of both originally by Arnold, Falk, and Winther, and in follow-ups by Martin Licht in 2018. And the key idea, if we haven't seen it before, is that here I've got, for instance, from the periodic table, full polynomials, polynomial degree 3, form degree 1, and these degrees of freedom that are in the interior of the triangle are going to represent the degrees of freedom of the trace-free functions. And if you pick them out and you go and you look elsewhere in the periodic table, like if you go look at the trimmed polynomials, you end up seeing that they look like those degrees of freedom. And that's not accidental. And it's not incidental. It's very important. We have this important isomorphism that the dual basis for the interior degrees of freedom for the full polynomials, well, that's going to be the trimmed polynomials that are unrestricted. And the trace-free trimmed polynomials, their dual basis, well, that's going to be the full polynomials unrestricted. We have to reduce the degree, the polynomial degree, and I'm putting colors in to highlight that you end up taking the dual form degree. So lambda k goes to lambda n minus k. So you should think of that as like HDiv goes to HCurl and HCurl goes to HDiv. So these are probably one of the best publicized ways that you see finite element exterior calculus out of the original work by Arnold, Falk, and Winther is that you can define the degrees of freedom for projecting into these full spaces by taking integrals with trimmed polynomials, and you can define the projection into the trimmed polynomials by taking integrals with the full polynomials. So that duality is very important. So there's something clearly innate going on there that may not be special to one space or another, but nevertheless, if you look at the literature, there are kind of separate constructions for full and trimmed polynomials. So if you want to construct trace-free full polynomials and you go to Arnold, Falk, and Winther, they take you to take a Whitney form with index sigma and turn it into a lambda sigma d lambda sigma star. So one of those trace-free things based on a barycentric K-form. And if you want to construct a trimmed polynomial, so like Ravière-Thomas, you take a barycentric K-form, sigma, and you instead, so you go the opposite direction. You go to kind of a bubble Whitney form. So the construction is direct mapping from Whitney forms to barycentric K forms and vice versa. So important thing to note about these definitions that you see in these works is that these are overdetermined, right? Because we're specifying an operator based on inputs and outputs of size n plus 1 choose k when the size of the space is only n plus k. So this is like trying to specify a matrix with more than n squared indices. So first you have to show that h and h minus exist. It's not clear from this presentation of these isomorphisms whether these operators are pointwise or not. So for instance, if I evaluate a K form at a point, there are multiple ways I could represent it at that point as the sum of multiple Whitney forms. So it's not clear if this is a pointwise operator or not. And if it's not pointwise, you have to use a particular basis. And the other thing is that we had this nice weight function in the scalar case, and there doesn't really seem to be anything that indicates a similar weight function here. And finally, one thing that's also still not clear from these two different constructions is, are they the same on the same input? These are nested spaces. If omega is in both spaces, is h of omega equal to h minus of omega? Okay, so I was trying to clarify that for myself when I was working on this work. And the first thing that surprised me is that we have this k n minus k duality. Why isn't the Hodge star being used in these constructions? So like, for instance, in 3D, we've got this pretty clear thing where I can take the Hodge star from dx1, dx2 to dx3. Why doesn't the Hodge star appear in any of the definitions on the previous slide for constructing maps between k and n minus k forms? And the answer is that the Hodge star, while it's an isometry, which is kind of its motivating thing, it's not affine invariant. So essentially, as I'll show on this slide, if I take the Hodge star of a vector, and then I transform both of those vectors, but then I take the Hodge star of the original vector again, I'll get two different vectors for that dual. So the Hodge star can't transform from reference to real elements. And so it can't be used for this k to n minus k duality that shows up in the trace-free constructions that we want. So one of the first things that you can do is you can actually define an analog of the Hodge star that's specific to each simplex. So the idea here is that this is a map, an isomorphism between n minus k forms and k forms. So you can just substitute h curl and h div and back and forth in your head if you want to. But the idea is instead of specifying, for each barycentric form it maps to this, this construction is kind of like a sum of outer products, right? I take omega and I take the K form that will turn it into a volume form. So again, that's kind of that volume form duality I mentioned a while back. And I'll take the star to turn it back into a scalar, and I'll multiply it by the same index form. So this really is like an outer product of like d lambda dot omega times d lambda. So if you do this, you end up with something that's like the Hodge star, but it's affine invariant. And you can actually show that it's equal to the Hodge star if the simplex that you do this for is an equilateral one. So as a simplex transforms back and forth, the Hodge, this star no longer always looks like just an equally scaled 90-degree angle. The angle is going to change, the length is going to change, but it also doesn't depend on the coordinate system. Okay, so once you have this type of construction, this outer product construction, it leads very directly to a way to do the unrestricted to trace-free construction. So here we've got the map from n minus k forms to trace-free k forms. And it's the same type of outer product structure, kind of d lambda dot omega times d lambda. But the only thing I'm doing now is I'm inserting a complementary bubble function in there. So if I've got this complementary bubble function, each of the things I'm summing up is trace-free, so the total thing is trace-free. So this operator is defined for all differential forms, not just full or trimmed polynomials. It's got this sum of outer product approach as opposed to being overdetermined, like in the original representation. It acts pointwise. And that scaling constant out front is just to give us this neat property that if I take this ring star operator twice, it's essentially just going to give me multiplication by the triangle or tetrahedron's interior bubble function with, some kind of a sign convention. So it turns out that this operator is essentially equivalent to those two operators that were shown as distinct in the original representation. So H minus took a barycentric form to a bubble Whitney form, and it turns out that ring star does too, with just a difference in the sign convention. And H took a Whitney form to a bubble barycentric form, and it turns out that the same operator, ring star, does too. So those two original H and H minus were essentially equivalent up to a sign. They were pointwise. It was just kind of obscured by the different presentations, as though they were distinct concepts. There's actually one single isomorphism at the heart of both of them. And not only is there an isomorphism, but like the case that I really wanted for in scalar, from the scalar polynomials, it defines a weighted L2 inner product. So if you take the inner product of omega with ring star applied to mu, and you integrate over the cell, you get something that is it's a weighted L2 inner product, and it's going to define bi-orthogonal basis, dual basis pairs in the full and trimmed polynomials. And so that thing that was floating around in the title slide, this is the indicatrix for that weight function. So the weight is large in the middle, and it gets smaller at the edges, but it gets smaller just in the normal directions at the edges, and then gets all the way small at the vertices. Okay, so what is the utility of this ring star operator for different approaches? I mentioned 3 of them at the start. Let's go through them again. If you define your finite elements just by dual basis decomposition, then the main utility is that weight function. If your dual basis is orthogonal with respect to that weight, then ring star is going to be the Riesz map. It's going to take you directly from a dual basis functional into a primal basis. If you're already using Bernstein polynomials, using ring stars is not really going to be much simpler than what you're already doing. So not really a lot of utility if that's your code. If you've got scalar code that uses Dubner type bases, then using ring star is going to be kind of a generalization of the construction used in the Sherwin and Karniadakis basis. It's going to take that basic idea, and you can use it for all K forms. So that is the presentation of the contribution in the trace-free unrestricted isomorphism. I'm going to talk about the extension operators next. I know I have passed the hour, but I don't want to use up too much of that in the actual talk. Let me stop though and see if there are questions before we start talking about extension operators. So any questions about this ring star operator or what I showed in this part? Okay, if not, I'm going to talk about the extension operators next. So it's not as accessible as the portion about the trace-free construction. Oh, and of course, a summary is that this ring star operator is an isomorphism of the trimmed spaces, of the full spaces, and of just differential forms in general, regardless of whether they're polynomial or not. Okay, so the second step of geometric decomposition is the extension operator. So we want to, in the scalar case, we extended, we multiplied by a bubble, and that got us an extension that could be used for as a basis function that was locally defined. So similar extension operators exist in the literature, those citations I gave. But they're even less unified than they were for the trace-free construction. Here we've got the extension operator for trimmed polynomials, and it basically looks like if I've got a barycentric monomial, excuse me, a Bernstein monomial and a Whitney form, I kind of pull back to the equivalent Bernstein monomial and Whitney form. But the construction is much more difficult for full polynomials. You have the product of a Bernstein monomial and a barycentric form. And to do the pullback, you have to do a particular projection operator to pull back in, for instance, from an edge into a triangle. So these operators, because they're based on Bernstein bases, are definitely not pointwise. So you can't apply them to general differential forms directly. You might have to do some kind of an expansion. And they're definitely incompatible. So a K form would be pulled back differently by these different operators. So just to very quickly show how we can build a universal extension operator. Recall that things that are trace-free are not necessarily vanishing on the boundary. They can have perpendicular traces. If we take all of our trace-free functions, we can decompose them into portions that have one portion with perpendicular trace for every boundary facet. So for facet F, you would have some sort of data that lived on the facet, and you would pull it back, and you would wedge it with that facet's bubble function and a complementary barycentric K form. And it turns out that that will give you something that's trace-free, and it has perpendicular trace only on F, or a super simplex of F. So just to show what I mean, here we have a bubble Whitney form. So it's trace-free, even though it has perpendicular traces. The bubble decomposition would break it down into one which has all of the perpendicular trace on this edge, and one which has all of the perpendicular trace on this edge. So that's basically what's going on here. You can evaluate this bubble decomposition even if you don't have a bubble decomposition basis that you're using. And in fact, you can't have a bubble decomposition basis for the trimmed forms, for instance. These things that add up to a degree 1, or I guess in this case, a degree 2 trimmed polynomial, are not themselves degree 2 trimmed polynomials. So you can evaluate these even though they're not a basis. It's still a pointwise operator, but you do have to, for instance, evaluate projections onto subsimplices, order 1 of them, in order to evaluate a function in terms of its bubble function decomposition. So it turns out that once you can decompose a trace-free function into this bubble form, each of the bubbles pulls back in a fairly natural way. If it was a pullback into F of omega E, it will be a pullback of omega E into T. And where you had a bubble for edge E in, for instance, facet F, it would now just be a bubble for E in the main triangle or tetrahedron. And likewise, the barycentric K-form on F would map to a barycentric K-form on T, the full triangle. So this decomposition is not new to my work. It turns out that this is a generalization of the hierarchical basis from Ainsworth and Coyle, where they talk about edge-based face functions, edge-based interior functions, or face-based interior functions. These are essentially the bubble decomposition that I'm talking about. So the fact that you can do a bubble decomposition for all forms, that's not really surprising. The fact that this bubble decomposition is a decomposition of the full polynomials, which is what the Ainsworth and Coyle space was defined for, that's not new. What is kind of surprising and what is new in the work that's up on arXiv is the fact that it actually preserves the trimmed polynomials as a subspace of the full polynomials. And just to give a sketch of the proof of how that happens, this map of each individual bubble function, each individual bubble extension commutes with the COSL operator, and the COSL operator is very intimately tied to the definition of trimmed polynomials. So because it commutes with the COSL operator, it's going to preserve the trimmed status, is it trimmed or not, of each individual bubble. And so when we combine them all back together, it also preserves trim status plus some lower order polynomial. Okay, so that was a bit faster because the portion on extension operators is a bit more technical. It doesn't give me as nice, fun, nice GIFs to do. So what is the utility of this universal extension operator? Well, if you're already doing a dual basis decomposition to define your finite elements, you're already not really evaluating extension operators directly, so there isn't really utility there. If you're using a Bernstein basis, it's not really going to give you utility unless you really are interested in preserving the trimmed full subspaces. If you're using Dubner type polynomials, it's a pretty natural fit. One problem, though, is that it's hard to do sum factorization for all of the edges. So it's not a problem in the dimensions that we care about, up to 3D. You're not going to increase the complexity too much. You'll still have the same complexity as if you were doing sum factorization, but you would increase the complexity if you went to higher dimensions, like 4D or something like that. And there are simpler operators, extension operators that you could use for trimmed polynomials if you wanted to. So although the extension operator is universal, it's not really the simplest one you would use in all cases. Okay, so this brings me to essentially the final summary of the paper up in arXiv, which is we have two operators, one that is the isomorphism between trace-free and unrestricted forms, and one that is the extension operator from a boundary facet into the interior of the triangle or the tetrahedron. And we just had to define one, and it gave us a geometric decomposition of all K-forms. And it also gave us a geometric decomposition of full polynomials. And the same operators gave me a geometric decomposition of trimmed polynomials. And they're pointwise. They can be done in that decorator pattern that I talked about. So if you're trying to have a small code base that can do finite elements by explicitly defining trace-free functions and extension operators, this is an approach that's going to give you a very small code base that will cover a large variety of mixed finite elements. So that is the material of the talk. Thanks to everyone for the attention. I'm right at an hour. So again, thanks for the opportunity to speak here today.
You mentioned that you can develop a very nice finite element, compact finite element code with based on these ideas. Do you have such a code or examples of such codes that people can play with?
So the interesting thing is that, so like I said, the code that I work on, PETSI FE, is one that's based on dual functionals, and I construct the inverse van der Waals matrix. So this whole thing started off simply because I was after that weight function. It was the thing that I wanted out of it. The trace-free operator is implemented in the slides. So if you want to see the way that the figures in the slides are generated, you can see that trace-free operator. I don't have an implementation of the extension operator to share. I had hoped to kind of have that also in the slides, but other stuff came up this past week.
Understandable. And this is this all works both in 2D, 3D, and even more, right? You showed some examples with triangles, but also some with that.
Yeah, and you know, like I said, the complexity of these operators isn't always going to be the best if you wanted to go above 3D, but it's certainly a valid construction for arbitrary dimension, arbitrary form degree. That's one of the beauties of the exterior calculus approach, is that if you were trying to do, you know, space-time elements for some sort of a you know, people do Petrov-Galerkin space-time things for stability, you could use this there, for instance.
Okay, thanks. I have more questions, but I'll wait.
I think you can go ahead with your questions, Nanyo.
Yeah, please.
All right, I don't want to monopolize it. I was wondering, so we usually use in FEM, we use nodal basis. We don't do hierarchical stuff yet. Do you have any opinion on the different degrees of freedom for nodal basis functions on simplices?
So
Different sets of
nodal,
degrees.
yeah. So for nodal basis, so I didn't have this in this talk. Let me quickly pivot to the one that I did a month ago. So yeah, you can construct all of these. So for instance, you can construct projection operators that respect that weight function, but that's going to be kind of a modal projection, even if you were using a nodal basis. But a nodal basis that I've worked with that is, where did the actual presentation of it go? Here it is. Just a second while the slide spins up. Okay, so when I need to construct nodes on a simplex, there are obviously papers out there where you can find people who have numerically tried to minimize the Lebesgue constant by the placement of the nodes. That's more common. I've seen that done in 2D. I haven't really seen that published for tetrahedra yet. So I wanted to have a simple way to define nodal bases for simplices that would give me reasonable scaling for the Lebesgue constant for the interpolation error. I took classes from Tim Warburton when I was an undergrad, and so I was kind of aware of his warp and blend bases, which have been around for a while. And it turns out that they are very similar in 2D to a construction where you use the spacing based on like Gauss-Lobato points, not only for like the placement of nodes along the edges, but they kind of give you the weights with which you combine contributions from the different edges for the interior degrees of freedom. And so I've got this very simple Python code that defines arbitrary order nodes in the interior of 2D, 3D, I guess any D, but no one really needs higher than 3D. Like I said, it's very close in 2D to Warburton's warp and blend nodes. But in 3D, it gives better Lebesgue constant scaling than any of the other explicitly defined families that I know of that are published out there.
We have something similar actually in FEM. Vesselin is unfortunately not here. It's not published. but it's in the code.
Okay. Yeah.
And it does use exactly the weights from the Gauss-Lobato or whatever quadrature rule you have on the edge to extend it to the interiors of the faces and the edges.
Okay. Yeah. So the definition is kind of just recursively blending them together, and the blending weights are themselves kind of the Lobato node locations. So they serve kind of double duty as nodes and weights. And so that's what we use in PETCFE right now. And short of doing the numerical optimization of the Lebesgue constant, I don't know that you're going to get a lot better, but it still is not going to get you what's sort of known to be the case, that you ought to be able to find some optimal nodes where the Lebesgue constant will eventually scale linearly or sublinearly. It's not really there, but it's good for practical orders.
All right, right. Yeah, very, very interesting. This is very interesting. Your talk was great. Thanks.
Oh, it was like I said, it's a great chance to talk to people about this subject matter. My students are interested. I don't have as many finite element people to talk to on a day-to-day basis, so I maybe went a little bit overboard.
No, that was great. Let me go one more, and this is my last one. Okay, I can
No,
talk
no problem.
for a long time. You mentioned sum factorization a few times. Do you, in your practical experience, do you know when sum factorization actually pays off for simplices?
So I'm not the person to ask about that, right? So the Paul Fisher people doing NEC 5000. I mean, it's obviously going to depend on the architecture of when you're going to be able to get vectorization payoff, particularly for those warped Dubner type, right? Because you do have some factorization, but you kind of have to bring in a separate matrix for each different kind of column of points in the nodes when you do that. What is it? That strewed conical map between the triangle and the square.
Yes.
And so you have to be able to vectorize over enough elements to make up for the additional memory traffic compared to like the Bernstein approach, where it's sum factorized and you don't have to bring in assembled matrices. So it's hard to give a when does it pay off answer when you're not talking about a particular machine, but they would know better than I would.
Yeah, thank you.
That's a good question.
Sure.
Hi, I'm Andrew. I actually went to UT. Also, I graduated 2011, so we may have overlapped a little. I can't quite remember, but your name sounds familiar. I really enjoyed your talk. I've studied a lot about finite element exterior calculus and that kind of stuff. I was curious, everything you said was about simplices, which are obviously important and a particular case. And now there's recent work by Arbogast, for instance, about trying to use barycentric functions to define base functions on quads, even arbitrary quads. Are you thinking about going in that direction at all? Do you see any opportunities there?
I haven't thought about it in respect to this work. I'll kind of give you my one kind of quad and hex related thing that I've been thinking about recently, which is I don't know if you're familiar with the recent work that Lee and Winther have done. They've generalized this approach that Wheeler and Yotov have done for a while, where like if you're doing Darcy, you technically have a flux space that's there, but you put the degrees of freedom in the quadrature at the corners, and so you can kind of compress out your flux variable, and you're left with a finite volume, right? This is mixed flux finite elements, or something along those lines. And so Lee and Winther have generalized this, up the de Rham complex, and some of Yotov's students have also generalized it to higher dimensions. And so I don't think it's going to give you kind of the robustness of, with respect to geometric distortion as the Arbogast approach that's got kind of the non-reference element constructions with the barycentric bases. but it does, it does give you nice tensor product operations up to higher order. But these spaces are kind of interesting to define. I think they're called like the augmented serendipity spaces, because they kind of have the serendipity spaces plus some additional ones that you would need to get kind of a tensor product set of nodes. And I think that it's possible to say that these spaces are all nice and well and good, but you can achieve the same thing if you do essentially a filter operator on the differential. So the idea being you would use the spaces that are not actually on the de Rham complex going to be exact, but if you apply a filter to like the div operator, the curl operator, I think you can end up with something that is going to be, essentially the same matrices that you construct as these ones that have the kind of correct spaces.
What do you mean by filter?
So I guess the idea is like I would use a representation of the flux that is not exact. The divergence is not onto L2, but wherever I see divergence, I would first project into a space that is exact with my L2 space, and then take the div. So it's sort of like I only want the div of the part that matters in terms of mapping onto the L2 space. I think that you can say with some of these constructions that kind of variational crime gives you some of the same assembled matrices as some of these fancier spaces. So it's something that I've kind of worked out on paper but haven't really investigated completely. But I do like a lot of these ideas that use the mixed analysis and then get you back to a simpler thing in implementation. Get yourself back to a finite volume for Darcy, and in this case, get yourself back to tensor product spaces that are easy to work with. And so that's kind of the one quad and hex idea that I've got at the moment.
Interesting. Thank you for the comment.
Mm-hmm.
Any other takes?
It's fine if that's all. This has been a lot of fun.
Yeah, we also saw a few people leave at around the hour mark. Yeah, Daniel, you wanted to say something?
I just want to mention that the website has been updated and there's a link to your slides now.
Great.
Toby, so people can go and play with this themselves.
I look forward to feedback, and you can do a pull request on the slides if I got something wrong. I'm fine with that.
Oh, that's cool. I like it.
Okay, I think we're gonna wrap this up. Again, thank you for volunteering on presenting, and again, this was very nice mix to see on the rest of our application, heavier presentations, and now very theoretical talk. I really enjoyed that.
I'm glad I could help in that respect. Thanks again for the invitation.
And we'll be back next week. There's another talk on
right
now that Thomas is going to talk about space-time hybridizable DG.
Perfect. All right. Thanks again.
See you, everyone.
Thanks, everyone.
Thanks, Toby.
Have a good day.
Take care.
Bye-bye.